Dear colleagues, thank you for inviting me to this workshop. Unfortunately, I was unable to come in person, so I will talk in effigy. So the topic of my talk is weak solutions and the Lambert principle. So let me start from weak solutions. Weak solution is defined as follows. It is a vector field u of xt such that it satisfies the following integral relations. Integral u dv dt plus u tensor u gradient v dx dt equals 0. Integral u gradient phi dx dt equals 0. Weak Euler equations. Here V is a vector field C0 infinity, which is incompressible, and phi is a scalar function. Here we see no derivative of u, just u and product of components of u. So this means that a priori u is just in L2, which is the most natural space for this problem. I skip different questions of history of this and cite the most recent result is the theorem, which was Deleuze. Hidi is it Buchminster. Proved this year that for any function e t in C, e of t non-negative, there exists a weak solution u of t such that its energy integral 1/2 u xt squared dx is given function e of t, which is called energy profile. So there exists weak solution with arbitrary and it is the first claim. And the second thing, it is the most important, that u xt c 1/3 minus epsilon of 0 t times domain where the fluid moves. It's all in three-dimensional space. So this settles the most interesting and important part of the Onsager's conjecture, that the natural threshold of the energy conservation is Hölder 1/3. So for solutions which are less regular than Hölder, it is possible that the energy changes. Here it really changes in an arbitrary way. So this way the Onsager's conjecture is settled. But I don't think that Onsager would be happy with this solution. He was interested in physically meaningful weak solutions, which are limits of a viscous solution when viscosity goes to zero. For such solution, energy decreases. So this makes suspicious all the such solution where the energy does not decrease and increase sometimes. More important is the following thing, which we can infer from looking into construction of this solution and all other weak solutions which were found up to now, starting from the work of Schaefer. All these constructions are based on the following lemma. Suppose we have a sequence of functions satisfying the following thing: uk dv dt plus uk cross uk gradient v dx dt equals fk, and integral uk gradient v dx dt equals 0. So uk are solutions of weak solutions of Euler equations with right hand side fk. And suppose that uk go to u strongly in A2 and fk go to 0 as distributions. Then u is a weak solution. So in all these works, in all constructions, we constructed the sequences of solutions with some right-hand side, and this right-hand side goes to 0 weakly, means it becomes more and more oscillating, and possibly there is also some concentration. Currently, it is unclear what can be said, what can be called a limit of these forces Fk when they weakly go to 0. If we would be able sometime to define it, now we consider it just formally, limit Fk when k goes to infinity, then this u is a weak solution with right hand side f. F is a strange thing. It is some force or a function or vector function which is orthogonal to all smooth functions. But if you substitute it into the right hand side of Euler equations, it produces as a force some considerable and measurable motion of the fluid, so it is not 0. And so all these strange weak solutions are produced, are moved by these strange forces, which sometimes called ghost force, sometimes ephemeral forces. So we cannot say that they are true solutions. In fact, most of them are fake solutions. But among them there exist really interesting turbulent solutions, such that this force is just infinitesimal friction force between infinitesimally small, infinitesimally close fluid particles. And the problem is how to to find these really interesting weak solutions among the sea of these fake solutions. In this talk I wanted to describe some ideas how can we do it. Okay, let me consider geometrical picture of the flow. Suppose we consider the motion of the fluid in some domain M in Rn. Now, M is a bounded domain with a good boundary. So let us consider the set, say, denoted by D, otherwise it's denoted by S diff M. The set of volume preserving diffeomorphisms of M. This set is naturally embedded in the space L2 from M to the whole Rn. So any diffeomorphism is a map into the ambient space. Let Ft in D is the trajectory of the fluid. So the fluid flow is described by family time-dependent diffeomorphism. It's Lagrangian description. Then this Ft is satisfies the D'Alembert principle, namely Ft in D, Ft dot in Td tangent space at the point Ft, Ft double dot acceleration is orthogonal to T Ft d. So if you open all brackets here, then you will recover the Lagrangian, then the Euler equations. The problem is that this set D, when it is put in the physically meaningful space L2 and in Euclidean space, it should be completed there to become closed. It is non-smooth, and the notion of tangent space of Ft dot and Ft double dot remain also unclear. Now, the degree of smoothness of this set can be characterized in part by the following statement. Here is the set D in our L2 space. Consider two elements of D, F and G, and consider the arc distance between them along the paths going in the space D. Then distance between F and G is less or equal than C times F minus G in L2 to some power alpha. In case n equals 3, alpha is somehow 2/7. No, I proved it some considerable time ago. So this space is far from smooth. So all the notions here should be clarified or somehow reformulated. Now Now let me describe the general setup. Consider set gamma in Euclidean space E. Let us, and we are consider the motion of a material point along this set gamma. So it is non-smooth, arbitrarily non-smooth constraint. How can we describe it? First, we construct some approximate discrete trajectory. Let us take point x0 in gamma, and let us take initial vector u0. It is initial velocity. Then I propose the following construction. Let us fix tau. I define the point y0 equal x0 plus tau times u0. Here is y0. Then let me define it y1. I define x1 is projection of y1 onto gamma. Projection means the closest point. So this is, it is y1, and this is y1, and this is x1. So we define the point x1. And now let me define further points. x2 equals x1 plus x1 minus x0. So we connect x0 and x1 by a segment and continue the same length further. y2. x2 is projection on gamma of y2. This is x2. Now we continue further. This is y3. Take the closest point, which is x3, and so on and so on. This way we constructed a chain of points x0, x1, xn. Now n equals t divided by tau. T is the whole time interval. And then we try to go to the limit when tau goes to 0 in all this construction. Now say we connect these points x0, x1, x2, and so on by piecewise linear path. Yes, so it is union of some number of segments. And then look if you can extract from these segments, these paths when to go to 0, we can extract something, some limit or at least limit point. This is maybe tricky, and the only case when it was successful is when gamma is convex set. Limit exists. Now, the interesting case of this situation is the description of ideal inextensible thread. So consider the motion, free motion of a thread, inextensible thread, so its linear density is 1 in the space. It is described by the position of this thread is described by the function x of s in Rn, and gamma is the following, that dx ds less or equal than 1. Why less or equal? Because the thread is inextensible, but nobody said that it is incompressible. It can be compressed by infinitely small coils. So gamma is this set of such positions. And for this situation, for this case, we can really define this way the weak solution with really weak solutions. No, I have no time to discuss the properties of this solution. I wanted to consider just one example. The motion of the whip. Let us fold the thread like this, so that one half is moving, say, right, other half part is moving to the left. Then the part moving to the right will elongate, the part moving to the left will shorten, but the total energy and the total momentum will be the same. At last, all the energy will be concentrated at infinitesimally small segment of this part of the thread. And then this principle, where it really works, says what will be next. So next, at some moment, say t equals t1, we have this configuration, just a segment, and then it turns out when t is more than 1, when t1, it remains the same. So all the energy will somehow dissipate from this end point of the whip. Unfortunately, this strategy does not work for the fluid. And it does not work in general for non-smooth and non-convex set gamma. The reason is that in the case of convex gamma, the length of every next link will not be bigger than of the previous one, so the speed decreases. However, here for the fluid, this set D is far from convex. It is not convex, not locally convex, so we have no control over the speed, so nothing works. And this requires some more tools, which I will now describe. Okay, suppose again we have gamma in E, and for any x in gamma, we have the surrogate tangents space fx. Now we want to define a trajectory of a material point moving along this set gamma. So let us consider this trajectory x of t. Trajectory. And this trajectory is defined by generalized D'Alembert principle if it satisfies the following conditions. First, x of t in gamma. Second, x of 0 equals x0 in gamma. X dot of 0 equals u0 in f at the point x0. Second, x of s, x of t equals x0 plus integral from 0 to t u of s ds. U of s is always in the tangent space at the point x of s. And for the most important, u of t equals ordered project s between 0 and t, projections of on the subspaces f at the point x of s. And all this is applied to u0. Now, what is this thing? Ordered product of projections. Let us consider the following moments: s0 equals 0, less than s1, less than sn equals t. Now here sk equals k tau. Let us fix tau. Fix it. N equals t divided by tau. And consider the following product. P projection at the subspace at the point x0 times projection at the subspace at the point x of s1, f at the point x of s2, and so on f at the point x of Sn. And all this product is called Q tau, and depending on t. And then it is natural to define a limit. Projection of fx of s equals limit when tau goes to 0, q to t. Now this limit, in what sense is taken? Does it exist? No, in general, it may not exist, and we have to extend somehow the notion of the limit. And the most powerful universal extension is using the non-standard analysis. So let M star is be the non-standard model of the mathematical universe M. No, mathematical universe contains all numbers, spaces, functions, and so on. M contains infinitesimal. So, let tau be a fixed infinitesimal. Then projection f x s t is by definition we have to take q t tau with infinitesimal tau, which is well defined by the general principles of non-standard analysis, and take the standard part of this, which exists and is finite. Now, simply because the norm of q tau t less or equal than 1 for any finite tau, and so by the transfer principle for any infinitesimal tau. And in this situation, this is a finite number in the non-standard, finite non-standard operator. No, in the worst case it is 0. And then it has a standard part. So this is a definition of this product. Now, this definition includes a lot of arbitrary elements, namely the non-standard extension M and the infinitesimal tau, which depend on uncountable set of arbitrary choices. This means that most probably we will have non-unique trajectories, and the degree of their non-uniqueness is somehow parameterized by these non-standard models. So here we use a non-standard model and infinitesimal as parameters. No, it is unusual but not impossible. So why not? So now I wanted to consider one elementary example which shows how it works. Let us assume that E, for example, E equals R2, and gamma is a rectifiable curve in E, which is parameterized by parameter S, x of S, such that dx ds equals 1. So S is a natural parameter, and in this case the unit normal vector is defined by the angle theta of S with the x-axis, and we assume that theta of S is a typical realization of the linear process. So what does it mean? So consider the quadratic variation. Consider some theta of sk plus 1 minus theta of sk square k from 0 to n. No, this means that s between goes between 0 and t. And this goes to simply t for maximum sk plus 1 minus sk goes to 0 almost sure. So typical realization is a realization where this happens. So with probability 1 we have a typical realization. And then the projection on the tangent space, there is now this tangent line, it is not surrogate, has the product of this projection, then have has the following norm: P on f x of s x of s, this norm equals e minus t, e minus t over 2. So this means that the motion equation ds dt equals e minus s over 2 u0, no, absolute value of u0, s of t equals 2 logarithm u0 t divided by 2 plus 1. And ds dt equals 2 divided by t plus 2 divided by u0. So this means that velocity, the speed decreases, goes to 0 in some non-trivial way, as if we had some strange friction on this curve. This friction is a result of its non-smoothness. If the curve were less regular, say theta as a function of t belongs to some Euler space with exponent less than 1/2, then the motion will stop immediately. So whatever initial velocity, the velocity at any positive moment is 0. If it is more regular, then the speed is constant. So here we got exactly in the threshold. Okay, now all this literally goes through in case when gamma is not very regular surface, say a surface having a tangent plane at every point, but this tangent plane, its direction is some Euler function on the surface. In this case, all these constructions go through. I cannot say the universal answer. It becomes much more meaningful, but I assume that in this case there exists severely non-unique solution. Okay, now let us turn to the fluid. Consider domain again M in Rn, and we consider the motion of the fluid in domain M. Now let us assume that volume of M is 1. In general, if you consider weak solution, it's non-regular. So trajectories of particles are not unique. They can collide, they can stick, they can they can split, can do whatever. So the classical picture where the motion is defined, the motion is defined by the motion of fluid particles which are attached to their initial positions, is not valid now. So we have to introduce a separate space of fluid particles, omega, space of fluid particles. Now omega is endowed with some sigma algebra, which sets of fluid particles are measurable, and probability measure mu. So we have this classical triple omega f mu, which is a classical probability space. Now, fluid configuration where each particle was is a map f from omega to m. Measurable map, now we consider Lebesgue measure in m, and it should be incompressible. Incompressibility means that f, the image of mu, is Lebesgue measure in m, incompressibility. And the set of admissible configuration is defined by psi. Psi in L2 of M Rn. Now, which is this ambient Euclidean space E. Now, let us define what is the surrogate tangent space. If you have f in psi, consider the function v of omega, omega element of omega is fluid particle, so velocity of fluid, such that they are equal almost everywhere v of f of omega, where v in L2 of M gradient divergence v is 0, v n on dm equals 0. No, this in the L2 sense So all these V are all such V which satisfy this form a linear space which is F at the point F small. This is the surrogate tangent space. I would say that these spaces look more like a distribution of subspaces along the set psi capital, but we have what we have. And now we have all the setup which I explained before. So we have F depending on T. Omega. It is flow. It is the motion of fluid particles. And we require that F of T in C for all T in our domain. Now F of 0 also in psi, and F of T omega equals F of 0 omega plus integral from 0 to T V of S omega ds, and where V at the point of T equals product of order product F of S here it is times V of 0. So this is the requirement on our solution. So it is justified by the definition justified by the following theorem. If F T omega satisfies what? 1, 2, 3, 4. Then V of xt, let me write, V of omega t equals V of F omega t t, and V xt, this is x, is a weak solution of Euler equation. And the energy integral 1/2 V xt square dx is non-increasing. So this way we constructed a weak solution, and I hope that it is more physically reasonable, simply because we had some physical input. Currently, I am not able to prove existence of this solution under the general conditions, but hope it will be done soon. Thank you for your attention.